All right, we're back, and today I'm going to do a small explanation beforehand, and then I'm going to continue by writing an expression parser for our little recursive descent parser. So, as you all know, but just to, summarize it again and maybe make clear what terms I'll be using, when you have a mathematical expression, or rather any expression in a programming language, you have what is called precedence. And precedence is the order in which certain operations should be performed. So, for example, in this case, we have 4 plus 5 times 3 plus 1. So the naive approach that some programming languages, like for example Smalltalk, take is to say, okay, I have a 4, so I add 5 to that, which is 9. And then I multiply that by 3, which is 27, and I add 1, which is 28. And but what mathematicians say is in English it's called the BODMAS rule. In German, since we usually use a dot instead of the asterisk for multiplication that the programming languages use, we usually say dot before dash. So that means division is usually a colon, so 2 dots above each other, not a slash like it would be in C. And so since we have dot and double dots to indicate multiplication and division, you can say dot before dash, and that means plus and minus, which are all dashes in some way, or dot before line, I guess. So that's what we use. So in summary, multiplication and division have higher priority. So to correctly execute this code, you would have to say, first I'll do 5 times 3, which is 15. Then I add 4 to it, which is 19. And then I add 1 to it, which is 20. So a completely different result. So now that seems so easy if you just look at it. But like, how would you do that in your parser, without looping, like going through the entire expression and kind of going like, okay, here, I guess this is the first one. And now how do I keep track of putting the result in there? And which of the others do I do first? Ideally, you would still want to be able to mostly read it left to right. And you can do that. Because one thing that you should think about is that any operation here written in an operator like this with infix notation, so like with the operation name in between its 2 arguments, can of course be rewritten. So you could just have a function multiply that takes 2 arguments, 5 and 3. And now if you look at a function that is called multiply and has 2 arguments, 5 times 3, that almost looks like the constructor for a C++ object that is called multiply. And yes, you could create a simple object that takes a left-hand side argument, a right-hand side argument, and the name of the operation to perform. And that's basically what our parser will generate in the end. A tree of these objects. Again, we've had a tree for every function, so this is just another function. So how would you do that? Well, what we do is we assign a precedence number to each of the operators. So I don't know, plus has precedence 1, which is the lowest precedence. Minus can have the same precedence. It doesn't make any difference what order you perform additions or subtractions in mathematics, at least. It might be a little different if you're dealing with floating point maths or something, but it will be good enough for us. And then multiplication gets a higher number, let's say 10. So what do? We have a function that parses a single value, which is the left a number, either an integer or a double, and we have a function, and we will now later add a function that will just loop, like get the first value, then check is there an operator after it. If yes, grab another value and then create an object from that. So that is basically one thing that you could do. And then it will note down, like it can tell from this object, from its operation name or whatever, what precedence number it has. So it will remember, okay, this has precedence 1. So it will then check, okay, I have one simple expression. Maybe it is a longer expression. So it'll check, is the next character an operator? And if it is, it will say, okay, what precedence does this? Well, first it will grab the next value. And so now it will know we have an operator and a value. That means we can extend this expression. Then it will check what precedence number does this one have. And since this is 10 and this is only 1, it will go, oh, wait, this operator has a higher priority. So that means this number doesn't belong to the addition as I originally wrote it, but will actually belong to the multiplication. So it will grab this number, insert it into a new multiplication object that is 5 times 3, and will then just insert that object on the left-hand side of the addition. And that will look like this. So you see we have 4 plus, and then here an object 5 times 3. So far that's fairly easy. Of course, what happens if you now have another operation following that? Well, you remember, like, as the text was written out, the argument in question was always the rightmost one. So basically that's the interesting one. Always the last one parsed, and its right-hand side might change. Everything else might stay the same. So what you do is you look into at the first object, and it's an addition. This is an addition, so their level is equal. So it doesn't really matter whether you take the result of this and add 1 or another one. But there could be another addition here. So you go up until you have the rightmost one, and each time check what priority, what precedence value number does it have. This is 10, that's bigger than +1. So we definitely will not be able to steal this 3, which is correct, you know. And so what we will do is we'll go to the first value that is less than ours and steal its right-hand argument. It's just a depth first search through a tree, basically. But in this case, they're all equal or higher than us. So we'll just go, okay, it doesn't matter. We'll just plug this entire expression into our left-hand side, because we have basically the lowest priority in the expression. So that means we get this tree structure. We have a addition with 1 on the right-hand side and another expression on the left-hand side. We have 4 plus something in that left-hand side object, and in that object we have 5 times 3. Now, how do we evaluate this expression? Well, we just walk the tree. So we start at the bottom here, and this can be any C++ object that we define, you know, an expression object, or an operation object maybe. And so we just go, all right, we call evaluate, since each of these objects can be, you know, can do something. So what we do is we call evaluate on each of our arguments when you call evaluate on us. So basically you start at the bottom, call evaluate on the bottommost object, and that object recursively calls evaluate on its 2 arguments, and then once it has evaluated them and has constant numbers for them, it adds them together, and that's the result of its evaluate. So in this case, that means 1 evaluates to 1. That just stays the same, nothing to do here really. But here on the left-hand side, 4 plus something, that has some evaluating to do. So 4 evaluates to 4, so it already has that. But here is a multiplication, so when it calls evaluate on that, we end up in this case. And now this calls evaluate on 5 and 3, which are both literals, constant values, so we get a 5 and a 3 back. And then it has its values, there's no one else to call, so it will just multiply them to get you 15. And 15 will be the result it gives back. And then this one can do 4 plus 15. So this value gets removed and collapses as well. We get 19. That is the result of this call to evaluate, and then this object has 19 plus 1, and so this will return 20, and you have the result of the expression. So that's basically how you would evaluate this expression that used to be written in one single line as 4 plus 5 times 3 plus 1. So that's really all there is, I'm saying. Yes, I know it might take a moment to get your head around this, especially how you parse it. But basically the general rule is assign priorities to all your operations, no matter whether they're mathematical or something else. You know, many languages have a string concatenation operator, which often is the plus sign just operating with strings, or the ampersand or the dot operator, depending on which operator isn't used in the language for anything else. So there's really all those operators. You just have to have an order for each operator so that if several of them show up in an expression, you know which one goes first. That's basically it. And then you just scan from left to right. Like, basically this is our parse number function that does the entire expression. It parses one number, checks if there's an operator after it. If not, then you just get a single number, not an expression. But since there is one, it will parse the 5, as we did earlier, and then it will just keep doing that, you know. So you get the first value and then get any additional values concatenated with an operator. Not really that much to do, but maybe it will become clearer once we write the code. But I hope that this introduction is kind of helpful in this case. So here we are. We have our program from previously, and this time, after 2 episodes, I noticed that I tested everything in this way. So when I had my talking head here, it was an empty space. It was fine. But as soon as you run the code, of course, this pane pops up, and I can see it here fine. I don't see my talking head. So I didn't notice that the head was covering everything here. So now it's on the right, where hopefully it will not cover as much. But this is the result of what we did before. We created our parser. It can parse a function. It can identify that there's a variable declaration with initial value 1.5, which is a double. And it can call a printf function containing this format string and a number. And that runs through. But of course, what we want to do now is we want to be able to parse this expression in there that we originally had in there. So how do we do this? Well, first we go back to our parser class, and here we have expect one value, which just grabs a single value. And the first thing we should do is change this a little bit, because we need a distinction between things that may show up in an expression and things that may not, and things that may show up on a line. and not. So as you see right now, we would perfectly fine allow expect variable declaration, not just expect function call. So what we're going to do first, let's just for testability, I'm not actually writing tests here for this demo. I probably should, rather I certainly should. So everything, when I basically modify the script and run it, that would be something that you would do in a test. So you would write a little source file for running all your tests. And in that, just say here, this string, take it, run it through our parser, verify that what comes out is actually the object tree that we expect. But I didn't want to, do all that object tree walking and things like that in this stream here. So that's basically left as an exercise to the reader, or maybe for a future episode if I feel I want to cover that eventually. But write unit tests, especially if you're writing a programming language, it keeps getting more complex and more complex. And if you've unit tested all your simple individual syntax constructs alone, then those are a solid foundation. And every time you build something, you notice when you break something in them. And you know that this new thing that you added doesn't just not break anything, but also works the way you expect. And on the other hand, of course, you can, if you realize that you broke something and it didn't show up in a test, that's a good test to write. So that's something I won't be covering here. I won't be covering up how to set up testing in your IDE. But if your IDE doesn't support testing, it's totally fine to just put all your testing code in the main function here as you develop and make sure this code all runs through, because that's basically what I'm doing. This is the code I would need for test. In fact, I could even change this code so it will just run the given script and compare it to the output that I expect, and then make a loop that loops over all the files in a tests folder and just runs one test script after the other, and verifies that it matches whatever output I expect. Totally fine. But of course, that would then be a separate test executable that just includes all your parsers files. And this executable, of course, in the end is supposed to be our parser's executable, where you can just, point it at a file and it will run that script or whatever. But that would be the right thing to do, and I'm just saving myself some time here to get to the beefy stuff, because you can learn testing correctly from lots of people. There are fewer tutorials out there about how to create parsers and expression parsers. All right, so where are we? We have our parser, and it parses a few things too many. So first, we need a new function like expect function call or expect one value actually, and let's put it near that one. And we call it expect statement. All right. Again, we let our IDE just create the function for us. And now when we have, where is it? Expect variable declaration, expect one value. So now we need to call expect one value, and we need to call expect a variable declaration. Best copy the entire function body and delete the stuff we won't need. And expect one value, of course, shouldn't parse variable declarations, because those have no business in an expression, but a function call is correct. And now we'll paste it in here, and similarly here we'll do what is it? Result equals expect one value, and then here if not result has value, so if it wasn't a number or string, a literal basically, then we try, is it a variable declaration? And if we don't have that, well, it would also be a function, so we don't need expect function call either. So this expect statement is pretty nice already. And so now everywhere where we used to call expect one value, we will instead call expect, well, not everywhere, but like where we expected a statement and not just any value, we'll call expect statement. And I think that might actually be it, because this one, yeah, this one should be an expression inside the variable declaration. So that's good that that says expect one value, because we also now can't have variable declaration inside a variable declaration, which would be wrong, you know. And here, where we're parsing a function call, of course, each argument should be a value. So that's that can stay this way as well. We don't want a variable declaration inside the parameter. And I think that's still the function call. Yeah, that's just the same one. And then we're back at expect statement. So now we have modified it, but it should run just the same. Oh wait, it will probably not run. Yes. Because we got an error. Oh, one thing I should probably do, because we're getting crashes, of course, is we should log any exceptions we encounter, or rather we throw. Catch standard, what is it? Exception. And we log them to see error and say error, and then error.what, just so we see what we're doing. And in all other cases, just to be sure, like if we run out of memory or whatever, we'll log unknown error. And we should probably end the line as well. Okay. And maybe we say return 2 and return 1 here. Be a good Unix citizen and only return 0 on success. All right, so if we run this now, let's see what it says. Expected comma to separate parameters. That's a bit of a surprise, but interesting. Mistakes are always interesting. So let's run that in the debugger and see what happens. Well, let's find this. And run it and see where we are. Current token. is an operator. But I can't actually read what the operator is, which is a bit annoying. So where are we? Expect statement. Well, let's be a little more expressive and actually log what we're finding. So string plus this plus a dot. And now here we say current token text. So this, in this spot, really what I should be doing is check that we have a current token. Left as an exercise. Because, you know, we could be getting, we could be at the end of the program. So let's rerun that and see what the error message says. Let's just keep it running. Minus. Okay. Yeah, okay. So that is actually correct. Because, yeah, okay. So it was actually what I expected. I just didn't expect this error message, but it makes sense. So of course, since here I didn't write 25 like we had before, so now it should just run through still, yes. So that still works, although we changed how the parser runs through. But we have now the distinction between a statement and a value. But now the thing is, these parameters are actually not just values. They are expressions, and this one also is really an expression. So that means it could contain operations. So how do we do this? Well, first we'll find our expect function call, and instead of parsing, and so we will add a new expect expression method. And what it does is, at first we just parse the left-hand value and return the left-hand value. That's all we need right now. Now you're unhappy, create it, yes. All right. And now we'll call expect expression in the spots where it makes sense for us to call, to want an expression, not a value. So expect one value, of course not. But here, that's the variable declaration. That should expect an expression, because you can declare a variable and initialize it to 5 times 5 if you want to. And here, expected an expression as parameter. That is our function call. Same here. And I think that's it. Yes. Well, actually, no. And here, where it expects a statement, it should also expect an expression, because, like, you can have an entire expression on one line. For example, here, this is an expression. it is result equals, that's an operator, and then a function call, which is just part of a value for us. So that totally makes sense. And actually, what I haven't told you yet, a function call, that's also just an operation, really, because like in our parser, we expect the function name to be an identifier. But if you've ever used function pointers in C or C++, you know that this doesn't have to be a function name identifier. It can just as well be any other variable that contains a function pointer. And in fact, that is all that a function name is. It's basically just a global variable pointing to the code. So it's also just a function pointer. So if you were to continue writing the parser, what you would also do is that for every value, you would say, no matter what the value is, if there is a set, if there is an open and bracket after it, it's probably a function call. And then you would parse the arguments and generate a function call that operates on whatever the left expression, whatever function pointer that returns. But, you know, that's beyond, and our little trick right now, just going with identifier, will be enough for us for now. And, you know, this is basically a postfix operator. Although you could probably just treat it like any other operator, as long as you remember to also, you know, parse the closing bracket afterwards. Because, you know, it is a value followed by an operator. So you can, for some users, treat it the same way and just remember this was actually a function call, and then do the closing bracket when you hit it. All right. Here we are, and now we can write our expression function. Well, first, let's run this once again. It still parses. So now we write our new script and finally go 2020 minus 1995. And now we go into the parser and start parsing this. So we have our left-hand side value already, and that is what we'll return, and that's totally fine. You know, that is what in our graphic, you know, was how we started. And now we say while expect operator, and here any operator will do, really. We don't expect any particular one. Although I guess we'll have to say while true because we want to remember our operator. So optional token operator, expect operator. Oh, and this is a reserved word, so let's just call it op. All right. So now we say if not op has value, then break out of the loop, which is important, because we have to do that at some point anyway. And otherwise, we will go and say, okay, we need to parse the right-hand side. So that's basically the same thing as expect one value, get an RHS, expect one value. Oh, and of course we want to remember if not LHS has value, then return null opt. Let's actually put these brackets here. It's always too easy to make errors. All right, and now if there is no right-hand side, then what we do is that's the end of the expression. Apparently we parsed wrong somewhere. Maybe we caught a, postfix operator or something. So what we will do is we will say return LHS, but of course we also need to backtrack over the operator. So that's the current token backtracked over. So that means that, because we already consumed that operator and didn't hit this case, so we have an operator that we shouldn't have eaten, and then we found out there is no value after the operator. For example, if it's a closing bracket, then of course that would be a problem. All right, and now we need a way to save an operation, and that's fairly easy because our statement is a function call. It has a function call, and the function call can have an arbitrary number of parameters. So that means, hey, we can just call a function representing this operation. And it doesn't have to compile to a function, but conceptually it's the same thing. They're all instructions at the end. So we'll just say, okay, we'll parse this for now as a new function call. So statement operator call. Did we give statement a constructor? I don't think so, no. All right, back here. So operator call name equals op text. We need to remember the name of the operator. And the nice thing is, since operators are names that the user cannot type in, we actually have no problem, with we have no problem with colliding with any names the user gave, because those would be an extra token and would not be a valid identifier. So there cannot be a function named asterisk. So we can just call this, create a operator call for this, and put, so for an easy start for now, we'll just put operator call parameters push back the left-hand side, and the right-hand side. Why are you complaining? Oh, it's an optional statement, so of course we need to do value. That's why the type mismatch. Okay. I should have probably read out those error messages. I hope you got to read them before I closed them. But basically it just said that the type of LHS or RHS was not the type of elements in M parameters, which is statement. And so of course they're optional statement. I need to unpack them. All right, we've already checked whether they have values, so here and here, so that's not really a problem. And now that we have rescued LHS and RHS, we can do LHS equals operator call. So we've basically grab the left and right argument from being a single statement struct. So statement struct is really not quite the correct name anymore because it's a value or a statement, but we're using the same type right now. It's fine. We're putting that into the left-hand side. And now if we looped over this again and got another operator, then it would use that expression, that entire expression, as its left argument. So that is basically the case we would need for parsing operators of a lower or the same precedence. So for example, in our example, the +1, that case we have now coded. And so this should parse now when we run it. And it does. It says, oh, of course, now we have a problem. We're eating any operator that we encounter. So that means we parse minus and comma as operations together. And of course, comma doesn't have, since we always assume it's a lower precedence, comma now ends up with the higher precedence. So comma has the string and the first number, and the 1995 is in the outer minus function. So I guess I should reformat that for a second so you can read better what happened. So here we have I think we didn't. We're also eating semicolons now. Yeah, so you see our parser is a little over-eager. So because we have a function call semicolon now, but semicolon should be the end of the statement. So let's not reformat this right now. And go back into the parser. So we need some way to find out, is this an operator? And so we say if not op text, if not is operator text, then do the same backtrack here. Oh, but actually, yeah, it's the same. And return the expression as it has been so far. And of course, we want to create the isOperator function. It should really be a const string reference for efficiency. All right, operator name. And now we say if operator name compare minus equals null, return true. So far that's good enough for us to parse. We can add additional operators here later. Oh yeah, I guess we don't need to use compare since we just need equality. Thank you. Nice compiler. You're actually making me use more efficient code. All right, now let's run that again. And it should now not parse stuff as badly anymore. Yes, it looks much more correct now. Because we have a lot of things that we parse into operator tokens that aren't operators in an expression. Okay, and now let's look at what it has parsed so far, just so it looks a little better. So we have our variable declaration, of course, which is just assigning 1.5 to it. So that, as you see, has not changed. We still get just a literal double. We don't get like a expression statement or something with only one argument in it or something. So that's great. Now we have the function call printf, which contains a literal, and it has a function called minus, which in turn contains the parameters 2020 and 1995. So that is exactly what we expected. We have, let's make it like this. So now you see, you have the printf call that goes until here. It has 2 arguments, and this argument has 2 arguments in turn. So exactly what we intended to parse. It's a nice, clean hierarchy. So yeah, success. And you know what? I'm gonna take a slight detour, I think. So here's the thing. You know, I declared a debug print. And now we add an indent parameter. That means that we can get this indented and I don't have to do it manually every time. And so let's go into statement and add the indent parameter here as well. And now how do we prefix this so it will be indented? Well, that's not much of a problem because string has a method we've been using already, which is the indent and a character. So like it's not indent, it's just the number of character, but it will, so far we've always passed 1 here, and now we just say, well, pass how many indentations there will be of this character. So we'll insert a tab and it will nicely indent it by 4 spaces to go with that. And we can actually, let's leave it like that. Okay. And so that's a space, the type name, and the end of the line. Okay, and now here we say debug print indent +1. And that will help us a lot while debugging, because every other statement that we print out will be indented by 1 more. And so if we now run the code again, we made a syntax error. Oh, we're not calling it the right way yet. So here we'll just pass 0, but that was intentional because I wanted it to tell me about that. Otherwise I could have given a default argument to this. Oh wait, I forgot something. In statement debug print here, this one, whoops, needs to be indented as well. That's why we're getting these silly people over there. Okay, and now you see it's much more readable, because now we have function printf. Oh, right, this is because the string has a return character at the end, of course. But anyway, this makes sense. And the string, of course, doesn't have any arguments. But as you see, we still have our minus operation inside the printf. So everything is fine and a little more readable now. And the same for the variable declaration. And I guess we should do the arguments. So function definition should print the parameter, and the parameter size t indent. All right, and now we need to fix size t indent here as well. We're probably only calling this in one spot, but just in case I forgot, I'm calling it elsewhere. I wanted to not make it a default argument. Okay, and so this gets indented by 1 because everything here is indented by 0. So now we should have up here, yeah, these arguments are indented as well. It uses 8 spaces, but it's fine. All right, quick detour, just so we'll have it cleaner in the future. In general, I encourage you to make all your output useful when you're parsing this stuff. You know, add debug print methods like this, because it's always easier to debug things if you have a function like this and can actually see your data structures. And as you see, the debugger doesn't always show you everything. Sometimes you will just not see the contents of a variable or things like that. All right, back to the parser. Our isOperator function. Let's give it a few more operations. Not that we have them yet. Multiply and divide. But really, no, we won't do it this way, but rather what we need is we need a priority for each operator, right? So let's define operator entry that is a string name and a number precedence. And well, that's actually all we need for that. And then create a global variable, or rather static, it's only inside this file. Operators. And put an operator entry in there. So plus is precedence 1 and minus is also precedence 1. We don't really care. And all right, no, I did it wrong, really. Although I guess this is okay, but we don't need an array. We want a map, of course. Map string to operator entry. And that, of course, means we need to tell the map about its key as well. So that's why the plus is doubled up here. All right. Oops. Come on, how did I re-indent again? code. Where is it? Reformat. Okay, that's nicer. Anyway. And oh, of course, those two should then be divide, multiply, divide, multiply. So divide and multiply are precedence 10, and plus and minus are 1. That looks fine. We have, you know, the entire space of a number of a size t, so we can afford to, you know, have like gaps in between, and maybe if we one day come up with another operator or something, it might be helpful to use the precedence in between if we want it to be, you know, lower priority than one but higher than another that already exists. Otherwise we'd have to edit them each time. All right, so we have this map, and now we can just go down here and say map, oops, all caps, map string operator entry iterator found operator equals as operators find operator name. So now we have found operator, and now we can say if found operator equals s operators end. So that means if we haven't found one, then we return 0, and that's just our magic number for the precedence now. And this will return an int, a size t actually, for the precedence. And otherwise it will return found operator second precedence. So now any operator we add to that list at the top will automatically not 0, okay, will automatically have will automatically be checked here, but we can also use that table for other purposes now. Is operator should of course return a size t in its header as well, just so that it compiles. And now of course here we actually want to remember the precedence. And that's the RHS precedence, the right-hand side precedence, of course. Wait, and if it's equals 0, of course, because then that means we didn't have one. And just to be safe, precedence 0 is reserved for no operator. Just so nobody gets the idea to use this. All right. And so now instead of, if we run this, it should run just the same, unless I made a mistake. Yes, it still runs the same. Good. So now our thing that we want to do now is, of course, do the actual precedence handling, which, as we said, was if the number is higher than ours, then steal the right-hand side of the rightmost operation. And this has two things that we need to look out for. First, we need to find the right-hand side that is closest to our precedence that we can steal from. And then we need to determine what precedence it actually has. And now I made a slight mistake here because I can't really tell the difference between an operator function and a non-operator function just by looking at a statement. Like, I have to look at its name. And that it is a function call. So what we'll do is we'll actually make it different after all. And I think that's all we should need. Operator call kind equals statement kind. Okay. Oh, and we need, wait, I remember now what I wanted to do. Oh no, but I don't need to write extra code because this will just work because I updated the string already. Yep, fine. I thought I'd have to write another if case here, but of course I don't because it's all this generic. So if I run this, all the difference that the only difference we should get would be that, yeah, this one is listed as operator call now, no longer as function call. That's all. And now we go into the parser, and we need to find the rightmost statement. And what do we need to do with it? We need to steal its argument and insert us in there. So all we need is really a pointer to the rightmost statement. Optional. Wait, optional pointers make no sense at all because they can still be null. So it's just statement pointer most statement equals statement of LHS and with RHS precedence. I'm not calling a statement. I guess I'll just create it by hand. It's fine. So just create a function. IDE is not quite smart enough. And RHS precedence is size t. And LHS really needs to be a statement pointer as well. In case we need to return that pointer. Okay. All right. created that function in the header as well. So we're all fine. So now what we will do with this one. So we will go if LHS kind equals operator call. Wait, if it's not an operator call, then we return a null pointer because we're done. That makes it shorter with an early exit. All right, and then we know it's an operator call. So now we go if LHS name is operator. That's a bad name, by the way, because it's no longer is operator, it's get operator precedence. So if operator bigger than RHS precedence, then again return null pointer. And else return not is operator, but actually rightmost statement. But it's LHS parameters, so the right-hand argument, and we need a pointer to that. Okay, but then we'll call this statement RHS, because if that is RHS kind, so if this is not an operator call, of course, then we're not returning a useful object. So in that case, we also return null pointer. No, wait. This one is same or lower precedence. So does it make sense? No, we shouldn't really return anything in that case. Right? I'm trying to come up with a good scheme for this now. So the thing is, I want to call this recursively to walk up the right side of our tree and find, you know, the statement with the with a lower precedence than us, the rightmost one. But I don't want to overshoot. So the question is, and we want something that we can steal the right-hand side argument of. So really there's no use in you know, returning anything that's not an operator call. But in this case, we know that it doesn't, so at this point we must have LHS, must have the same precedence as us. So we should just return LHS again here. And now, and we don't really need to do this. We know that it has a right-hand side argument. So we can actually just say RHS. Let's just yank this through here, reuse the variable, and say if RHS equals null pointer, then return LHS, otherwise return RHS. That should be right-ish. Why are you not happy? Oh, right, we need the RHS precedence here as the extra argument. Okay, let's remember if that is what I meant to do. So this will say if this is not an operator, then return null because it's useless to us. If it is an operator, but it has higher precedence as us, then return null as well, because that means it's the end. And then this one will say, we know that it's an operator, so we can get the second, the right-hand side, and then we'll call ourselves on that one. And so if that is a constant or something, then it will give us null back. So that means we need to return the left-hand side because it was the closest we could get. But if it's a if it's an operator that has lower precedence than us, it is already. So that means if the argument is nothing, then it will give us the left-hand side because that must already be the left-hand side, yes. So that makes sense. Oh, I think it's right. We'll see when we use it. And let's just refactor, rename, operator precedence. Better name. Okay, and now we go here. Why are you not happy? Rightmost statement. Term does not evaluate. Oh, it has the same. Okay, let's call this RH stumped. So it doesn't complain. No, we just call it RHS. Oh, and LHS s is an optional. LHS.value. Okay, what are you complaining about? Oh, we already have an RHS. Yeah, okay. Right most. Let's rename this to find rightmost statement. I just can't find a good name for the variable with that name. All right. So now we have the rightmost statement. And now we say if we have a rightmost statement, which means there is an object with a lower precedence than we have, then we assign RHS equals rightmost statement parameters 1, so the second argument. So we copy this over. And then, or we can wait, no. What is this? So now I'm doing my head in myself, which is good. Because this is now the complicated part. We need to take whatever value is in the right-hand side of the rightmost statement and put it in the left-hand side of our new operation. And then put our new parsed value in RHS value. All right, so let's just make these completely separate, because otherwise I'll just try too hard making the code not duplicate. So rightmost statement parameter at 1. All right, and now rightmost statement and parameters 1 equals the operator call. So that means if we have a rightmost statement, we make its left argument this one, and we make the previous rightmost statement's right argument our operator call. Yes, that looks good. So let's just run this and see if we crash or anything. No, so far it's looking good. And now we modify our code and see if it still parses. So 1995 times 2, which of course for years makes no sense. But it didn't eat. Didn't we register the asterisk operator properly? Oh, we have it here. Okay, so I guess we'll have to go through the expression parser and see what it's actually doing, which is generally what you do. So expect expression. And we should probably go and set our breakpoint here, which means that anything that isn't an expression should already have jumped bailed out, like the 1.5 here. Of course calls parse expression as well, or here the string calls parse expression, but really what we want is this one. All right, and here we are. What do we have? LHS is a value. It's a literal. Oh, the type is double. Okay, yeah. And the name is 1.5. Oh, okay, that's just an operator, but it doesn't have precedence. I was one too late. Here is where we should go. Because this, it's still an operator token. It's just not an operator we can do anything with. Okay, and now we have an operator that is a minus, so we're in the right spot. Okay. So we're, I think I can, horizontal and vertical, hard to tell apart. All right, so we have our code here, and as you see, so 2020, and it's actually usable, good. 2020 minus 1995 times 2. So we should have a left-hand side that is 2020, yes. So now let's expect one value, and that should be the RHS. And the RHS is 1995. So far, good. And now we find the rightmost statement, and I suspect that this is where it goes wrong, but we will see. Rightmost statement is null, which is good. And now we go here, statement operator call. Text LHS, RHS, and that replaces LHS. So that should be fine. So we should have 2020 minus 1995 in LHS now. It's a statement, it's an operator call, it says minus, and it has two parameters, which is 2020 and 1995. Yes, beautiful. So we have these. So the first round went correctly. And now we expect another operator, and it didn't find one. So what is our current token? That's an identifier. Where the heck does it get an identifier from? What is the text? 6. Okay, so I guess we'll just run it again and see. Alright, so first round was fine. And now expect operator is where it goes wrong. So step into that. I said step into that. Maybe not into all the system code. Come on, come back. Step out maybe a few times. Okay, now we're here. Current token equals end token. No, that's good already. Current token type. Current token type is not operator. That's not good. Did I not? Is the tokenizer wrong or what's going on here? Asterisk. So maybe backslash quote. Oh, I guess I just don't have the operator tokens yet. All right, let's see. If it's not a string, make an operator and end it immediately. Yeah, so I guess I can equals plus minus divided. Oh, I guess we had minus and that's why it worked so far. And I guess slash will work. So plus minus asterisk we have now. And we have slash separately. If it's a potential comment, then makes it a comment. Let's see if that works. But of course, if I forgot to do it in the parser, let's just keep it running, I guess. And see, it seems to have output something. Yeah, multiply 1995 by 2, that's correct. And that's the argument, the second argument to subtract 2020. So that's good. And now we say plus 1 just to see if that entire case still works. And it says plus. So it has, yeah, 2020 minus. $1995 times 2 plus 1. The question is that correct? Or should it be because plus ended up inside the Minus, does that make a difference? Not really, does it? Yeah, it doesn't, because if I do 2020, no, I think it does make a difference. Now I need to do maths, Jesus. Okay, so let's see, the thing is 1995 times 2 is okay to group together. And that gets subtracted, but the minus kind of belongs to the 1995 times 2. Not to the plus 1. So I think what we did wrong was that here we should say same precedence exits. And now let's run that again. Yeah, that's better. Because now we're taking the entire minus operation once it has completed and add 1 to that. Which, oh no, I guess it's the same, isn't it? Is it, let's see, 2020 minus, okay, luckily the computer can do maths for me because I didn't pick numbers that are 3990. Okay, so that means 3990 plus 1 is 3991. So 2020 minus 3991 is 1971 negative. And if instead I go 3991 is 9070 plus 1 is 1969. Yeah, that makes a difference. But this way it should go left to right. So I think that's correct. I remember doing it like that in previous ones, and it's a little bit important, like what you do with the precedence in the equals case, because basically what it does is it decides whether your operation is right binding or left binding. Like most common operations are left binding, so you execute the leftmost expression first and then execute the next one. So in this case you do 2020 minus 3000 plus 1. Because otherwise you would have to put brackets around it and say 1995 times 2 plus 1 and subtract that. As you said, it's a difference of it's a difference. Okay, so one question, I just mentioned brackets, so parentheses is what I meant. So like, what if I wanted to support this, writing parentheses around here in the upper right? Well, that's fairly easy, because basically what you can do is in expect one value, you can check, is the first token that I'm encountering here an opening parenthesis? And if it is, call expect expression until you hit the closing parenthesis, and then return that. And that way that expression gets parsed in its own context without, you know, the surrounding stuff that is not in parentheses. And that's basically all there is to it for, you know, supporting parentheses. So we'd go here and say here, else if what is it? Expect operator opening parenthesis has value, then result equals expect expression, expect operator closing parenthesis, or rather if not has value, then raise an error. Do we have an error here that we can just copy? Yes, it's faster to type that way. Unbalanced in parenthesized expression. Basically, that's all you would need there. Let's see, does that parse it correctly now? Yeah, and now you see the 1 plus 1 is now here, and the minus is now here. So that's all it takes. It's surprisingly simple once you've worked it out, that basically you just go, hey, parse this separately. And that's really all that parentheses mean. And yeah, that's pretty much all I wanted to demonstrate in this tutorial. That you can parse a C-like language with expressions and into a nice little tree structure. And now, of course, the magical thing that you would have to do to make this useful is to create a compiler that uses this parser, because we really only built something that gives you a data structure describing your program, that you can walk through and say, okay, I have these 4 functions or whatever, or this 1 function in this case, and I have you know, these kinds of expressions, and I parse them recursively. And to generate code for those is a little more involved. So first you need to decide, well, actually, if you want to generate code for those, that would be more complicated. And I think I'll just leave that out for now. But if you just wanted to run this code now, it would be a lot easier, because I'm not saying it's easy. I'm just saying it's easier than actually generating the code. I'm trying to avoid saying that things are simple and easy, because I know how hard it was when I got started. But they're, in general, easier than you would expect. And once you've, you know, managed to write one, it'll all seem obvious suddenly. But of course, not before that. I know that. I'm sorry. I'm sorry for all the pain you will be going through. But I hope that this video, these 3 videos, will actually help you a bit, because it's so much fun to actually write your own programming language. So what you can do is, as I mentioned at the start, you can have an evaluate function on each statement. And that just does the work that this statement should do. And so that means if the statement is a function call, for instance, so like our printf over here, what it would do is it would look for a function somewhere. And like, for example, we have in our parser, we have our mfunctions map. So what you could do if you just wanted to compile a single source file, and spoiler, your C compiler actually thinks everything is a single source file in some ways. So start with just making a programming language that can run a simple file. It's fine. There are ways to then graduate beyond that. And so it would just take that name, look it up in the mfunctions array, and then in the function definition, that one has a list of statements, and then you just loop over those and call evaluate on those. And each of these statements will do its thing. And again, you know, this is basically recursively as well, because you just call evaluate, and if that statement is another function, then again it will go into the mfunctions array, look it up there, look at its statements, and run them. You know, that's all it really needs. If it's an operator, then of course it will take its values, call evaluate on them, and then perform the mathematics like I described at the start of this whole video. Things like that. So how do you handle variables? So like, what if we wanted to allow foo? We haven't done that yet. Well, what you do is when you hit a variable declaration, you enter that in a data structure somewhere and say, okay, we have this variable. And again, it could be a map, you know, like the mfunctions as well. And then you can, for example, have a map for double variables, and then you just go and, like, everywhere where foo is requested, you check, is there a variable named foo? Well, there is no double variable, there is no int variable, there is no string variable or whatever, char, but oh, there is a double. In our list of double variables, there is one. And then you could just, you know, set the value of that map entry or something if you wanted to. You could have also, of course, also just have a map for all variables and make the variable entry a struct or something where you can decide, okay, I create a struct for the double or for something else, or you could make it a union. You know, there are different ways to handle this. Whatever feels right for you, just do it for your first language. It doesn't matter that much. Of course, because, you know, like, you're executing it all at runtime anyway, and, you know, parsing it all at runtime, so it won't be a super fast language if you just, you know, run the tree you parsed, but it will work, and it will be your first programming language, and there are many languages out there that just work that way. And you can then go over the code with a profiler and optimize it. So what do faster languages do? Well, basically, most faster languages are compilers, but they don't compile to machine code necessarily, but rather they create a little software program that basically does what your CPU would do, but in code. And this program is, of course, written like this parser in C++. And then you can and then you can write this little simulator and just write code that this simulator can run. Because machine code is nothing magical. Machine code is just an array of bytes. And those bytes have a certain form. So, like, the start of that, like, if an instruction is, I don't know, let's say 16 bytes long, then the first byte of those 16 bytes is the number, just a number identifying what should be done. So, you know, number 0 could mean, grab an int from memory and remember it in register 1. So registers are just variables. And then instruction 2 could mean, add the variable in register 1 to the value in register 1 to the value in register 2 and write it back out into register 1, for instance, or write it out into register 3, I don't know. But anyway, so you just have a bunch of predefined variables that you can use as scratch space, or you could even have your code directly operate on memory and just say, like, take the memory address or something. And so all you do is basically you create an array of bytes and append the bytes needed to describe the instructions, which you yourself make up. And they're basically tiny data structures that just all start with a number, identifying it what it is, and then depending on what instruction it is, contain the parameters, basically. So if you've ever learned programming in assembler and not just in C++, then basically you have seen a text form of that, at the least. And I would recommend that if you want to write your own virtual machine, your own bytecode interpreter, or if you want to write a compiler that actually compiles to native code, then you will have to learn assembler, because then you get a lot of interesting techniques, and you can write your first simulator. Could just be a simulator for a real CPU or something, or it could be a simplified form of that, because many CPUs have lots of historical baggage that's really annoying. But anyway, that's basically beyond the scope. I'm just trying to give you a bit of a lookout. I am thinking I'm writing my own virtual machine, or rewriting a virtual machine that I'm using in one of my projects, and doing some new experiments. So there might be streams or at least videos like this where I will actually write a virtual machine, and I might go deeper into how you would create, how you would compile code for that there. Otherwise, there is my domain compiler Bauhaus. So can I type here? No, that's the console. Let's just write that here. I think it's org or com. I don't remember actually. I think I might have registered both one. Anyway, it's compiler and then Bauhaus, like the art style. So it's a building house, basically a house for building stuff in German. But anyway, compiler Bauhaus, compiler building house. You can find short descriptions of certain things that you need when you write your own programming language there, so that might give you an additional outlook. I hope this has been not just completely confused, but also useful to you. It's just a little thing I wanted to do on the side to make it easier for people to make their own programming languages, because for one, I think personally I have a lot of fun coming up with my own language and trying out things where I think like, wouldn't it be nice if language X did that? And then I just create a language and play around with that and go, okay, that was a really stupid idea, and there's a reason why all other programming languages do it that way. Or I found out, hey, that's actually a clever idea, and I can actually maybe even simulate this in C++ or whatever language I'm forced to use at work, use similar approaches. So you learn a lot about programming and about how a programming language can work under the hood, which sometimes makes it more obvious for you why a certain programming language has a certain limitation. For example, I've always found it hard to understand why variables are, like fixed in size and things like that. And I have to do memory management if I want to use dynamic memory and things like that. In simple languages like C and C++, it's not as much a problem. And then when I learned assembler, I actually realized, okay, this is how the stack works. And since the variables are stacked on top of each other, you cannot make a variable larger or smaller. But of course, the compiler can hide all the memory management it does on the heap. So, because, yeah, and so just learning about all these innards of your computer can be really fun. And by writing your own programming language, you can do that. But of course, you don't have to go all the way down the rabbit hole. You can make a fairly simple language that just evaluates its own stuff and can fulfill a useful function in your program. For example, if you're making point-and-click adventures or something, they're not really performance constrained on modern computers. But there are a small set of very specific things that you might want to do in such a game. And so if you have a friend who doesn't program, but you're writing the engine for the game, and that friend would like to add some logic for the story, you can give them a simple programming language that they understand and that doesn't need to perform very well, because computers today are fast enough, and there will be only little bits of logic that your friend will write to support the game, and everything else will be running in natively compiled functions. And so you can just say, okay, if the command is, I don't know, set property open of door to true, then I'll just call set property with look up the property open in a table in the object and just assign the value true to that and call a certain function or whatever. Anyway, I'm rambling now. Have been for a while. So anyway, you can write programs and make give other people who are not programmers the opportunity to write programs in a language they understand. And that's what many domain-specific languages or DSLs are about. They're not about being a better general programming language, because we have some really good general purpose programming language. Actually, most of the modern programming language are barely catching up to certain programming languages from the 60s. Because there were some great ideas people had back then that nobody understood, and that everyone went like, well, they need too much CPU power. And now we have the CPU power, and people are slowly realizing, if we actually did the things the people had told us to do in the 60s, our code would be so much better and would have so many fewer bugs. But if you write a domain-specific language for, someone else to use on a project, then that's work you don't have to do, for instance, or that's work that people who know the problem space better than you can do without having to explain stuff to you every time. They just have to kind of make you understand the building blocks, and then when they have problems with something, you can say, oh, I can make that simpler for you. So that's it. I hope you enjoyed it. I hope you wrote your own simple parser in the time I've been rambling, or at least, in between watching these episodes of me talking needlessly long-winded. Have a great week. Have a great rest of your life. I don't know if you'll ever watch another video I made. But thank you, and I hope it was useful. And please make a programming language. There's so many cool things that you've probably thought of that nobody else has thought of, that you could add to a programming language. Have fun.